Hey geometry friends, today we are looking at chapter 4 and we're on lesson 4.3. We're going to talk today about congruent triangles. So you remember we talked earlier about the word congruent, and congruent means exactly the same size, exactly the same shape, exactly the same measure. So when we're talking about things that are congruent, we're talking about equivalence in size. But more importantly, when we talk about congruent, it means that they fit together. You can lay them on top of each other. It is in essence a copy, the same copy of another thing. So when we talk about congruent polygons, we're talking about polygons that have that characteristic. So if I were to draw, let's say, this triangle here and use my pen to make a copy and then paste it, what I've done is I've created two triangles that are congruent, right? Because clearly I can lay one on, I copied it, it's the same thing. I can lay one on top of the other. And so when I talk about congruent triangles, let's say I name this triangle ABC and I name this one GED, all right? If I do that, there are parts of these triangles that are not just congruent, but they're corresponding. So like this segment AB is a corresponding part to GE. Do you see why? Because it's the same length. Like when I slid them on top of each other, you knew that AB and GE went together. So they're corresponding parts. And BC, this side here, corresponds to ED, corresponds to segment ED, right? Let me put the little segments notation there. And then finally segment AC corresponds to segment GD. Now, the reason why this is important is because when I'm naming the fact that, let's say I want to say that these two triangles are congruent, I have to name them in the order of their corresponding parts. So for instance, if I were to say triangle BCA, right? BCA. I'd have to name this triangle EDG. I couldn't say GED or DGE because the sides would not correspond. So let me show you. BCA, I've got to do an EDG. Let me do an EDG. And what you'll see is, watch this, BC corresponds with ED, right? BC corresponds with ED. AC corresponds with GD, AC, GD. AB corresponds with GE. Notice that the order has to be exactly the same. So now I can say, oh, this triangle is congruent to this one because I've really made a point to line up the corresponding parts. This will be a little bit trickier, like if I had some other polygon, or even if I could have a triangle or something that's like that. This is not a triangle, obviously it's a pentagon. And if I have a pentagon like this, right, and I copy it and then I paste it, so I have this pentagon over here, I can take it and rotate it. And so sometimes when you have congruent figures, sometimes it's not as easy to determine where the corresponding parts are. So you got to really make sure you're paying attention. All right. All right. With that, let's look at a couple of examples and some more information. This figure is in your text. Just a quick look at this, just showing us that what a congruent figure is. A congruent figure will have the same exact size and the same exact shape, and the orientation might be different, right? And this looks like, I don't know, a sad fish or a sad drumstick. I don't know. Anyway, but this thing is, these 1, 2, and 3. They're congruent. Here, these guys look like they have pretty much the same shape, but they're of different sizes. They are not congruent, all right? So congruence means same shape, same size. You can fit them over top of each other. You might have to flip them around, but you can flip them over top of each other. In this section, what we are just talking about is what we did just a second ago, just talked about corresponding parts. Here they brought up something that I didn't, so I'm glad I'm looking at this. Corresponding sides, we talked about sides that are corresponding when you have two triangles that are congruent. We talked about the need to name them correctly, but I didn't talk about corresponding angles. And so basically, if I were to rotate this picture and slide it right on top, corresponding angles B would obviously correspond with J because they're equivalent, and then C would correspond with K, also equivalence, and A with H. And so they're showing what's a valid statement, what's not a valid statement, and notice the color coding here. The valid statement shows that you need to be sure that you are lining up the corresponding angles with one another, whereas the not valid statement doesn't do a good job of that. All right, so here's our first example. We're going to identify corresponding congruent parts. And so this figure right here, we should have several because we've got a 1, 2, 3, 4. We've got a quadrilateral, two quadrilaterals that are congruent. So show that the polygons are congruent by identifying all the congruent corresponding parts. Then write a congruent statement. So we can do that. Let's go ahead. So angle S is congruent with angle, which one has the 4? Angle D. And then angle P is congruent with angle G. Notice the markings. Angle Q is congruent with angle F. And then finally, angle R is congruent with angle E. So that's enough for the angles. Now we got to get the sides. So segment SR is congruent. SR has 3 stripes. SR, notice I'm going to say SR. I can't say ED. I've got to name it in the same order. So SR is congruent to segment DE. You see that? SR and DE. All right, I hope you do. I'm sorry. SP is congruent to SPDG. All right. Segment PQ is congruent to segment GF. And segment, let's see, I've got one more left. How about QR? That segment, QR, is congruent to segment FE. And so we have our list of congruent parts of these two quadrilaterals, and now we're going to name the two quadrilaterals that are congruent. So I'm going to say that quadrilateral, name this first one SPQR, right, is congruent to quadrilateral. So if S is congruent to D, then I have to write D, and P is congruent to G. I've got to write G, and Q is congruent to F, so I go with F, and R is congruent to E. I write E, and notice the congruent parts are named in exact order. So the quadrilateral SPQR is congruent to quadrilateral DGFE. So here we are given in this diagram in example 2 that triangle ABC is congruent to triangle DFE. And we're going to find the values of X and Y. So if these two triangles are congruent, then we know that their corresponding parts are congruent. Notice the naming ABC and DFE. So we can be confident that just as we see it, this angle is the same as this angle up here is equivalent to this bad boy here, and you get the idea. This guy here is this one here, and then the corresponding sides as well. So since we're supposed to find X and Y, I'm going to try to figure out an opportunity to do that. Here I've got this value is equal to this, and then this 2y plus x, the length of this side FE, has to be equal to BC. So I'm going to write those two equations down to get me started. So 8y minus 5, this upper angle, angle F, has to equal 99. And furthermore, side FE, that's 2y plus x, has to equal 38.4. Now that I've got that, I'm going to solve for y, plug y back in here, solve for x, do a little substitution. They are always trying to keep our algebra game uptight, but we're tough. So 8y is equal to, I'm going to add 5 to this side, and when I do that, I get a 104. 8y is equal to 104. I'm going to divide both sides by 8, and when I do that, y is equal to, let's see if I can do this in my head, 8 goes into 10 one time with a remainder of 2, 8 goes into 24 3 times, so y is equal to 13. So I've got one, I need to get the other. Knowing that y is equal to 13, I'm going to plug that 13 right into the equation for y. So I get 2 times 13 plus x is equal to 38.4. 2 times 13 is 26 plus x equals the same value before, 38.4. Subtracting 26 on both sides, I end up with 12.4. So it looks like my answers are y is equal to 13 and x is equal to 12.4. Let's stop and take a break and take a look at this theorem. It's called the third angles theorem. If you've got two angles of one triangle are congruent to two angles of a second triangle, then by golly gosh willikers, then the third angle must be congruent in the triangle. So let's think about this. I'm sorry for my silliness. Let's be serious. This is serious business. This angle and this angle, these guys are equivalent to this one and this one. Knowing that these three angles add up to 180 and these three angles add up to 180, and these, I've got two of the three angles being equivalent in two, obviously this guy has to equal this guy. Kind of makes a natural sense, right? So they're telling us that angle A and angle L are equivalent. And I hope just by what we said, you can think about proving that theorem, because that's a pretty useful theorem. All right, so let's look at example 3. We're going to use the third angle theorem. Party planning, another real world example. So party planning, the planners of the senior banquet decide to fold the dinner napkin using triangle pocket fold so that they can place small gifts in the pocket. If the angle NPQ, let's find that, NPQ, got it, is congruent to angle RST, and NPQ is 40, find SRT. So I like to literally write on my problems, so I'm going to do that. So NPQ is 40, so I'm going to write 40 right in there. And we are looking for SRT. We're looking for this angle right here. All right, so we're looking for this guy. I'm going to just put a little question mark there. All right, so I know that this is 40. I'm looking at this triangle NQP, and I'm like, oh, NQP, you got a 40-degree angle here. This is 90 degrees. I see what's going on. So I already know that I can find this angle here, and this angle is important to me because I think it's going to be a lot like angle R. I'm going to confirm that by going back to the fact that NPQ and RST are equivalent or congruent. So NPQ, and RST have the same measure, so that means that this guy is 40 degrees as well. Now, if I look carefully, I can see I've got two triangles. I'm going to highlight this one over here. In this, I don't know what color this is, kind of a peachish color. And then I'm going to highlight this guy over here. Let me use a smaller. You see these two triangles, guys? You see them? These two triangles are two triangles where two angles of the triangle are the same as two angles of the other triangle. You see where we're going. So this is 40, this is 90, this one over here has to be 50, and I'm going to write 50 not with a highlighter. It has to be 50 degrees. And if that's 50 degrees, check it out. This is 40, this is 90, this also has to be 50 degrees. So we found SRT, the measure of SRT is 50 degrees, and we found it by using the third angle theorem. And we've got one kind of long proof here that I think we'll save for the next video. So tune in for the rest of section 4.3. Thanks, guys.